extremity amputees to have autonomy and fewer limitations, most adopt the use of a prosthetic device. They mimic the function of a complete limb, allowing the amputee to move around more easily. Typically, these assemblies are made up of the prosthesis itself, a socket to act as the coupling between the limb and the prosthetic, and usually a prosthetic liner to protect the limb. However, residual limb tissue is not accustomed to these imposed loads, which can cause discomfort for amputees. Today, we will be discussing how we approach the problem of discomfort experience with the use of transtibial prosthesis. At the forefront of this project, it was necessary to understand the project's fundamental purpose by looking into the details of common problems experienced amongst amputees and how these issues have previously been approached. Once this was understood, we could move on to defining the scope and objectives of this project. This gave us the necessary framework to begin our research, which would later be followed by computational modelling and experimental validation. Discomfort in the residual limb of amputees is caused by high stresses and uneven pressure distributions when the load is applied, particularly when these high pressures target more sensitive areas of the amputated limb. Specifically, high compressive loads can cause pressure ulcers in the muscles under the amputated bone. However, the most common discomfort amongst amputees is more surface level. High shear and compressive loads at the surface of the limb and the interface between the stump and the liner can cause irritation, breakdown, and blistering. This is where stiffness tailoring comes in. By manipulating the material properties and structure of prosthetics, it's been proven possible to control how the load is absorbed. By aiming to have as much of this load absorbed by the prosthetic liner and socket as possible, the organic tissues of the amputee stump will experience lower stresses. This, coupled with a more uniform pressure distribution throughout the biological soft tissue, will maximise user comfort. With this, we concluded that in order to understand the level of comfort, we must investigate exactly how the relevant pressure and stress distributions can be altered by changing the material properties and structure of the prosthetic. Once we had developed an understanding on what the problem was and what had previously been looked into, we were able to define our project question and our scope. The purpose of our project was to analyse the interface between an amputee's residual limb and their prosthetic to determine the factors that influence the amputee's comfort. We defined our objectives to investigating the effects of varying the prosthetic liner and socket thickness and determining what effect this has on the stress distributions in the prosthetic assembly. We also aim to develop a more accurate and detailed model of the stump by investigating better non-linear material definitions than those that we had seen in the literature.
Now that our scope had been defined, we were able to plan the logistics of generating useful results. We began with simplified computational models and methodology so that both the models and results could be easily verified and understood. Then we stepped up to more complex and thus more accurate models and simulations. We began by modelling small cubes of materials we wanted to get more information from. This was how we decided on the constitutive models we wanted to use to define each material. Once this was decided, we were able to move on to the two-dimensional cross-section of a simplified assembly. Then, to see the effects that the complex loading situation may have, a three-dimensional model was created. Finally, we validated our results experimentally. Our two-dimensional model was a vast simplification of a realistic prosthetic assembly. The dimensions for each layer of the limb were derived from relevant literature, and the liner and socket were implemented as standard thicknesses commonly found in industry. As you can see on the schematic, we considered the amputated limb to be made of three layers. Firstly, the bone, and then a layer of muscle and adipose. This two-layered soft tissue is a step up in complexity in comparison to what has been previously done in the literature. We placed a high level of importance into developing accurate definitions for each of the materials used. The socket, liner, and bone material could all be modelled with linear elastic properties, assuming isotropic behaviour. However, the soft tissues in this model could not. A review of the literature showed that a more accurate description of these soft tissues could be achieved by using a hyperelastic constitutive model. We found that the Milne model worked best for our application, as this best replicated the small strain deformations we were anticipating. Through iteration and comparison to the literature, we were able to find the best modelling conditions to represent the real-world system. Firstly, the socket was constrained at a singular node to hold the model steady in space. but also to allow all components to deform. Additionally, the exposed faces were constrained in the longitudinal direction to stop it from expanding, which effectively made this a plane strain model. The load was applied to the bone, acting normal to the socket. This force was experimentally measured in the literature and occurs during the foot flat stage of the gait cycle. We developed a mesh which was refined throughout the adipose, liner and socket of the system, as this is where we are primarily looking to analyze the stress distributions. The three-dimensional model was developed in a similar way. The same dimensions used in the two-dimensional model were applied to form a three-dimensional limb model with a simplified, regular shape. The materials used in this model were also identical to those used in the two-dimensional model. This geometry allowed us to apply the more complex loading condition that was documented throughout the literature. A multi-axial load was set to act through the bone, again using the forces experienced during the flat foot stage during the gait cycle. The whole outer surface of the liner was fixed to mimic a rigid socket to reduce computational time, and we had previously proven that the significantly stiffer material of the socket effectively formed a rigid body anyway. This model allowed us to analyze the effects of downward loading on the near spherical base of a stump. The final model we created was an experimental model. We use this as a validation method for our computational models. As you can see, the cross-section is a replication of the two computational models. We used a 13mm diameter steel rod to represent the model's bone. Although this is significantly stiffer than bone, as bone has a much greater Young's modulus than the soft tissues, it acts as a rigid body in the system. The other components were modelled using gelatin, foam, rubber and PVC as previously completed in the literature. The experimental model was loaded at 2 points on either end of the steel rod, whilst being both vertically and horizontally supported on the base. Dots were randomly distributed across one face of the model, such that the model's strain could be accurately captured by digital image correlation.
All of the results taken from these models were taken as a stress in the direction of loading at the outer surface of the stump. Thus are insightful to understanding whether the limb is likely to undergo any skin degradation or pressure ulcer formation, which would cause significant discomfort to the amputee. It is difficult to quantify what magnitude of stress is required to cause damage due to the cyclic nature of loading associated with walking and the lack of quantitative data available in the literature. Thus, at this stage, any reduction in stress is being correlated to improved comfort. An investigation into the effects that varying the liner and socket thicknesses have on the peak stresses showed that a linear relationship exists with the variations in liner thickness. Although this appeared promising at first, practical implications limit the thickness that the liner can be. Issues with compliance and manoeuvrability would rule out the liners at the upper end of the tested scale, and additionally, the production of thinner liners would prove challenging. In comparison, socket thickness shows negligible maximum stress change with thicknesses higher than 10mm. This was expected as the socket is significantly stiffer than the other materials, so variations in thickness would not affect the stiffness distribution as significantly. This trend was also found when adjusting the socket stiffness, where a softer socket would result in less stress at the interface. However, this too sees practical limitations, particularly with excessive deformation of the socket. Similarly, the effects of the adipose thickness were also investigated. We investigated a thickness range which represented the physiological variation of amputees, documented through the literature. The effect had the same trend as the socket liner, however, interestingly, increasing the adipose thickness proved to be nearly 5 times as effective at reducing the maximum stress than the liner. This implies that the effectiveness could be improved by incorporating a hyperelastic element, as the adipose tissue does, suggesting that a silicone or bio-based material may be a more advantageous choice than the simpler foam that we modelled, and that they should be the subject of any further testing we complete. We also looked at the effects of altering the liner stiffness. As you can see, the max stress increases as the modulus of the liner increases, and can occur to a significant extent. Although the feasible range for the liner stiffness is much smaller than what we tested, and falls only within this circle, limiting the effect in user comfort that solely changing the liner stiffness can cause. Similar results were obtained from the three-dimensional model. Though, due to the increased runtime of these simulations and limited time frame available for this project, only the variations in adipose and liner thickness were completed, as this saw the most significant reductions in peak compressive stresses in the two-dimensional model. The three-dimensional model reinforced that the thicker both of these components were, the less stress the amputee's musculoskeletal system will experience. After collating all of our results, we were able to finalise our answer to the question, what variables had significant effect on the stress distribution? It was evident that the thicker the liner, the lower the maximum stress at the interface. Altering the stiffness of the liner did not show a significant effect, though we expect that coupling these two factors may amplify both of these effects. The socket had the opposite effect, where a larger thickness meant less compliance, which resulted in a higher peak stress at the interface. The thickness of the adipose had a similar effect to the liner, where maximum interface stress decreased with increasing thickness. Out of these factors, the thickness of the liner is the most accessible for change, particularly with the emerging possibility of liners being 3D printed so that they are customizable to the specific thickness required for the specific amputee. Though, until this becomes commonplace in the prosthetics industry, we can recommend that a thicker liner can be used to mitigate the problems for amputees who are experiencing discomfort due to compressive stress. Additionally, we can predict that individuals with a high adipose percentage will be less likely to experience this discomfort induced by compressive stress, as their adipose content is already acting as a liner would to protect the rest of their musculoskeletal system from damage.
Admittedly, there are many factors that we are yet to consider and simulate in our models. These include the use of more complex materials for the prosthetic liner, such as bio-based materials which have been successfully 4D printed and may offer an ability for the liner to respond to environmental factors, which is suggested to be hugely beneficial for mitigating these compressive stresses. Likewise, it has been indicated through the literature that a socket which has compliant areas corresponding to pressure-sensitive areas of the stump can significantly reduce stress in these areas where damage does occur. These levels of complexity fall well outside the scope and time frame of our project, but offer future ideas for improvement. To validate the discussed findings, we computationally modelled our experimental setup. Firstly, as we previously discussed, the material data of each simulant was found through individual instron loading. The same displacement was then applied to a computational model, resulting in displacements accurate to those measured. Following this, the assembled experimental model underwent destructive testing, that is, until the gelatin had such significant breakage that no useful data was being obtained. The first tear occurred at just over 1 millimeter of displacement. This is difficult to see in the image, but occurred in the circled region. This was due to tension and resulted in a brief drop in load carrying ability before the model returned to a similar stiffness as before. The next tear was much less significant and had a similar effect. The final tear had the largest effect. It occurred at around 7.5 millimeters of displacement, resulted in a significant model failure, and was the result of gelatin compression. These results are accurately replicated by our computational model, validating the application of these models to real-life applications. They are best replicated by the plane strain case as anticipated, as this represents the vast majority of our experimental model. Our computational model does not account for the small tensional failures experienced in the experimental model, but this is justifiable as we do not expect high tensional stresses to develop within the physiological prosthetic limb system. So now that we have thrown a number of results at you, let us summarise what we have learned. Through the literature, comparisons between our results and published data, and the steps we've taken to validate our model, we are confident that our modelling process does in fact provide results applicable to the real-life prosthetic limb interface. Yes, we have had to make many simplifications along the way, but each of these we have been able to justify. Of the factors we have tested, we have proven that it is beneficial to tailor the thickness and the stiffness of the prosthetic liner to maximise user comfort. Increasing the thickness and reducing the stiffness of this component reduces the compressive stresses experienced and therefore limits the chance of tissue irritation, breakdown, and blistering. Finally, we have been able to prove that the amputee's adipose layer offers cushioning to the interface alongside the prosthetic liner. From this, we can understand that amputees with a higher percentage of adipose may not require as thick a liner as amputees with a lower percentage. This once again reinforces the necessity of prosthetic components to be tailored to the specific amputee. This project would not have been possible without the support and guidance of our supervisors, Mark Battley and Simon Bickerton. We would also like to extend our gratitude to Made, Kariapa and Erin, who assisted us both in the experimental and computational sections of our project. Thank you all for listening.